Hello and welcome back. So we look at a problem dealing with the Brayton cycle. So it says an ideal Brayton cycle operating between the pressure limits of 1 bar and 8 bar has minimum and maximum temperatures of 300 and 1500 Kelvin. The ratio of specific heats of the working fluid is 1.4. The ideal Brayton cycle is an air standard cycle. We expect it to be air. So ratio of specific heats is essentially gamma, which is given as 1.4. So let's draw this cycle on a TS or a PV diagram. The TS is usually more useful for these kind of cycles. We have it operating between pressure limits of 1 bar and 8 bar. So the Brayton cycle, as we know, has two isentropic processes. So this is isentropic process 1 to 2, compression, constant pressure process, another constant pressure process, and we have expansion. So this is a constant pressure line. This is at 8 bar. This is another constant pressure line at 1 bar. This is some 3 and some 4. So it says the pressure limits are 1 bar and 8 bar. And the minimum and maximum temperature is 300 Kelvin and 1500 Kelvin. So if we look at this cycle here, this is the temperature axis. When we go up, we have increase in temperature. So the minimum temperature would be essentially this point here. So T1 is the minimum temperature, which is given as 300 Kelvin. The maximum temperature in all of these is this point over here. So essentially T3 is given to us as 1500 Kelvin. We are asked to find out the final temperatures at the end of compression and expansion. So compression is the process 1 to 2. So final temperature at the end of compression is T2. Expansion is 3 to 4. So we are asked to also find out T4. So this is the information given and this is what we are asked to find out. Okay. 1 to 2 is an isentropic process. So between 1 and 2, what we know is that we can write the pressure ratios in terms of the temperature ratios. So between 1 and 2, we have, for example, T2 by T1 is P2 by P1 to the power of gamma minus 1 by gamma. We are looking at temperature ratio. Often we get confused as to which should be on top, gamma minus 1 or gamma. What we know is the temperature ratio should be less than the pressure ratio. So this power should be less than 1. So this is gamma minus 1 by gamma. So this is actually quite a straightforward problem. So T2 is T1, which is 300, into P2 by P1, which is P2 equal to P3 equal to 8 bar. P1 is P4 is equal to 1 bar. So this is 8 by 1 to the power 0.4 by 1.4. So I can find this out. I am also asked to find out T4. I can write the same kind of expression, T4 by T3. P4 is 1, okay, this is 1 by 8. So this is what I need to find out. So I get the values of T2 and T4 as 543 Kelvin and 828 Kelvin. So that's all was asked in this particular problem. But we can look at other things. For example, if we wanted to find out, once we have the temperatures, we have all the state points, we know the pressures. So anything else which we wanted to, we could find out. For example, what we can find out is turbine work, we can find out compressor work, we can find out heat input, we can find out heat out rejected, and we can also find out efficiency. So since we can do all of these, just as an example, let's do it anyway. We don't know what is the mass flow rate, so we'll find all of this on a specific basis. So what I will do is I will write small alphabets. So the turbine work would be enthalpy at the inlet minus enthalpy at the outlet. Which for an ideal gas would be this. Compressor work would be enthalpy at the inlet of the compressor. I think I wrote that as 1 minus enthalpy at the outlet. The heat transferred, this is an isobaric process, would be the enthalpy at the outlet minus enthalpy at the inlet. Similarly, the heat rejected would be enthalpy at the outlet minus enthalpy at the inlet. So I can find out values of all of these. I have T1 is 300, T2 is 543.4. $828. CP for air is about 1005 or let's say 1004.5. This is in joule per kg Kelvin. This is about 1223 kilojoule per kg. This is about minus 244.5. It's about 960. It's about minus 530 kilojoule per kg. The efficiency is essentially the net work by the heat input. That's equal to sigma W by Q in. I can write this as sigma W and just sum up these two, or I can also write this as turbine work minus compressor work minus mod of compressor work by Q in. So essentially all the same thing. I can also write this as Q in minus, I can write this as sigma Q by Q in, which is Q net, or I can also write this as Q in plus Q out by Q in, or I can also write this as Q in minus of mod Q out, where I take the minus sign already, divided by Q in. I can write it in all of these forms, they are all the same. Or I can also write this as 1 minus the temperature at the end of compression minus the temperature at the, 1 minus temperature at the beginning of compression minus the temperature at the end of compression. All of them should give me the same value, which you should be able to check. So let me do this for example. So if I take sum of heats, I have 960 minus 530 divided by 960 which gives me a value of 44.8%. If I do this, I have T1 is 300 divided by T2 is 543.4, and I have to subtract this from 1, which also gives me a value of 44.8%. So I can do it, I can find this in many ways. So all of them give me the same answer. It was 7.9 in both these cases. I just rounded off to 44.8. This is a Brayton cycle problem where we do not have any non-idealness in the compression and expansion process. If we had some non-idealness because of which we did not have reversible processes, we can take those into account by taking into account the isentropic efficiency of both compression and expansion. So if this was non-ideal, this would go somewhere here, and this would go somewhere here, and I would have this new cycle 1, 2 prime, 3, 4 prime, for which I can also find values if I knew how far this deviation is, so that I would be able to take into account. So this is where we stop for today. Thank you.